Hello and welcome back to Precalculus. This section is on graphing other four trig functions. Last class we graphed sine and cosine, and today we have secant, cosecant, tangent, and cotangent. Now, let's first talk about secant and cosecant because those are going to go very quickly if you know sines and cosines. And then, completely unrelated, will be, unrelated, completely different way is going to be there for tangent and cotangent. So let's start with our secant, cosecant graphs. Before I do anything, I will remind you that cosecant x was 1 over sine x, and the secant x was 1 over cosine x. Well, that should tell you something immediately, right? If you want to graph if you're supposed to graph secant or cosecant, just graph sines and cosines and then flip them inside out. Which is why teaching secant and cosecant should take like 5 minutes. Now let's do a couple of examples, but still, it should be really quick. So let's take a look at a couple of examples. I'm going to immediately jump into our section in the homework and take, let's say, problem 40 because we can. So y equals negative 3/2. That's a secant pi x. That's it. That's the problem. Well, what you are going to graph is a cosine. And then you're just going to flip it. And I'll show you how you flip it. So you are not going to do the secant. You are going to do the cosine, and then we're going to flip it. So what do we have as specs? Well, a is negative 3/2. Well, sorry, not negative. A is 3/2. And then I'm going to put flip so I don't miss it, right? I can also do this, flip, right? The reason why I make sure, because sometimes you forget to look back and see if there was a minus there. So make sure it's flipped. And then we have our b, which is pi, and we have a c and d. We know we don't care if there is no plus something over here, so we know that the middle line is at our x-axis. Okay, so period is 2 pi over pi, which is 2. Okay. My start point is going to be pi x equals 0. Well, x equals 0. And my end point is 0 plus 2 equals 2. So x equals 2 is the end point. Wow, this is actually really easy. Now, leave yourself more room than what you had with sines and cosines, because the graphs are going to go out of those bounds. All right, so what do I have? I have 0 to 2, and I have the midline, and I have to go up 3/2. That's 1.5. Okay, so let's use 3 boxes for 3/2. There we go. So that's my 3/2 on top, negative 3/2 on the bottom, and I have my max line, midline, and so on. Now, the next order of business is to put the left and right. So since I picked my, well, I'm going to stretch it here actually. This is going to be my 1, and it's going to be my 2. And I have my blue box, as you can see. I need to put the cosine in this box, and it's flipped. That is the key, it's flipped. So these 2 points are on the bottom, there's one on the top, and then the halves are going to have this. Now, I am not supposed to have a cosine graph, so I'm going to draw that blue. Because remember, all of the blue lines you can just delete. So here's the cosine graph. Now the sad part is no one cares about cosine, right? We actually want the secant. Now, how do you get that graph? Well, take a pair of scissors and just cut along the midline and flip inside out. Now, when I cut through the middle line, first of all, anywhere where the cosine crosses the zero is where you have your vertical asymptotes. In my lectures, vertical asymptotes are always red. That's it. Now, the black points are anchors. So, there we go. There we go. And there we go. That's it. So what I did is I cut and I flip. I cut and the flip. So now, if I get rid of all of the blue lines, what you are left with is the secant graph. So I drew cosine, but then I just flipped that cosine out and I got the secant. That's all it is. So if you know how to graph a cosine graph, you will graph the cosine, and then whatever the cosine graph is, or a sine, doesn't matter, right? Maybe you graph some kind of sine that was shifted right here. You would put your vertical asymptotes through every zero, and you will flip these upside down. And then you will remove the sine, and you have a cosecant. So let's do one more of these. But as I said, they're very simple because you just have one extra step in addition to graphing sine or cosine. Just that flip. And then you can delete your sine or cosine that you used as a base. Let's see if we can find one of the cosecant problems. And I would like to see something, oh, here, perfect, something spicier. So 48 has a spicier problem. Y equal to cosecant of 2x minus pi over 2 plus 1. So that's problem 48. I'm going to graph sine because cosecant is 1 over sine. Sine is easy to graph. I know how to graph sine. So graph sine and then just flip it inside out. Okay, my amplitude is 1. The B is 2. D is 1. And your period is 2 pi over 2, which is pi. Your start point is 2x minus pi over 2 equal to 0. 2x equals pi over 2. X equals pi over 4, because half of pi over 2 is pi over 4. And the end point is start point pi over 4 plus the period pi for a total of 5 pi over 4. Now, you might be going, oh, fractions again. Again, I don't care about the fraction. I care that there is 1 pi over 4 here and 5 pi over 4s here. So 1 tick mark and 5 tick marks, altogether 6 tick marks. That's all I care about. Cool. So I have my values. Now remember, always leave yourself extra room, because not just that you have to shift everything up 1 unit, you also have to have enough room to invert your graphs. So I'm going to start right here. Then I'm going to say I'm going 1 unit up, and then I have to go 1 more unit up for the max line, and the old x-axis becomes the minimum line. Now remember, your job is to count to 5. So 1, 2, 3, 4, 5. That's what 5 pi over 4 is. And this is where pi over 4 is. So I just counted to 5. And that gives me left and right, which gives me the box for my sine function. It's not flipped. So my sine function starts here, goes through the middle, ends there. So go up, go through the middle, go down, go up, end up in the middle. The rule for secant cosecant graphs is anywhere where the sine or cosine crosses x-axis, you are going to have a vertical asymptote. Now, can anyone tell me why is that so? Why do we have a vertical asymptote through each zero, in this case of sine? Anyone? What's a cosecant equal to as the identity? I had it up there. You can't see it now, but I did write it. What's cosecant equal to as the identity? It's not a trick question. It's a basic identity. We covered it twice so far.
1 over sine.
Perfect. Now, do you see when sine is equal to 0, why cosecant has an asymptote? Right? The denominator is 0. So we have a vertical asymptote there. All of the mathematics has to click perfectly. Doesn't matter if we are discussing exponential, logarithmic, trigonometric functions. Everything that you ever learned has always to click and be there, right? No exceptions to the rule. So if we were looking for vertical asymptotes in 2.6 by setting denominator equal to 0, well, here it is again. Cosecant x will have vertical asymptotes anytime sine x has a 0, because sine x is in the denominator. And sine x has a 0 wherever it crosses x-axis. I mean, midline, technically, in this case. So all I need to do now, guys, all I did is I graphed sine. These are all the same steps that we did for graphing sine. Now, the step where this sine becomes a cosecant is where I go to the max and to the min, and I draw these. The blue line is no longer needed because the blue line was our sine, and there we go. The black line is the cosecant. That's all it takes. Flip them inside out. And that's it. That's the secant and cosecant. So just more of sine and cosine graphs. What we want to focus on are tangent and cotangent graphs, because those are using different formulas. Tangent graphs. All right, so the tangent graph it has to have vertical asymptotes, because its tangent is sine divided by cosine. So anytime the cosine crosses the x-axis, tangent must have vertical asymptote. So tangent x is sine x over cosine x. When you look at the cosine graph, which ends at 2 pi, you quickly see that at pi over 2, 3 pi over 2, on this side, negative pi over 2, you see that it has zeros. So that means that the vertical asymptotes for tangent occur, well, infinitely many times, first of all. They occur at every point where cosine has a zero. So if I want to draw a basic tangent, and we'll take the principal period here, which is from negative pi over 2 to positive pi over 2, we have to put vertical asymptotes there because cosine of these pi over 2's has zeros, as you can see, right? Because cosine has zeros, tangent, right, will have a vertical asymptote there. And now the tangent goes through 0, 0. I can't even draw anymore. There you go. And this is the tangent. It will repeat every pi one, two, 1, 2. And now there we go. So the tangent graph has infinitely many of these squiggles stacked to the left and to the right, going to infinity. And when you take a look at this graph, right, it has infinitely many vertical asymptotes. So vertical asymptotes are at x equals pi over 2 plus minus n pi. N is 0, 1, 2, 3, going on forever. So that's where my vertical asymptotes are. And it also has x-intercepts. And they happen at 0 plus minus, well, x equals 0 plus minus n pi, because this one is at pi, this one is at 2 pi, this one is at negative pi. So every pi units, it has these divisions. Now, over here, we don't have a start point and end point. You have the midpoint. That's what you have, the midpoint. And then the asymptotes are going to be half of the period to the left and half of the period to the right. So formula for period is equal to pi over b now. Let me put this in blood. Not 2 pi. It's pi over b. And the same will be for cotangent. So you guys have a whole bunch of, whole bunch. You have 4 trig functions whose period is 2 pi. And then you have these 2 functions that have period as pi. So you have the 2 values there. So that's the period. Then the midpoint is the argument equal to 0. So argument equal to 0. And the asymptotes are at midpoint plus half a period and midpoint minus half of the period. So this is all that you need for tangent. So you still have y equals a tangent bx minus c plus d. You still have the dubc at work. Make sure you do the d first, and then now amplitude you can't really do amplitude well with tangent, because it's just, how fast it kind of squiggles through. So does it do this or does it do that? Right? The question is just how quickly is gonna go through this. So amplitude really doesn't, it's not humanly possible to do a great job graphing the amplitude, but the rest, they're all visible and perfect. So let's say we have y equals -3 tangent of, let's just have x over 2 minus 2, whatever. So the big flip is here. Then amplitude equals 3, and I'm just going to cross that. B equals 1/2, and D equals -2. Okay. B will give me the period, so that's pi over 1/2. Ooh, I just made period to be 2 pi, right? And that's because we had x over 2, not because it has to do with sine and cosine. The period of the tangent is pi. And then through x over 2, you can force it to be 2 pi. Midpoint is x over 2 equals to 0. So x equals 0. And the asymptotes are going to be half of the period add on one side and half of the period subtract on the other side, so that the midpoint can stay in the middle. So vertical asymptotes, we have 2 of them for the principal period, right? The first one will be 0 plus 2 pi over 2, which is pi. And the other one is 0 minus 2 pi over 2, which is negative pi. Why do I have a ridiculous 2 pi over 2? Well, 2 pi is the period that we have, and we need half of it. Remember, there is the full period p in between 2 asymptotes, because the function repeats itself. Every period function completely repeats itself. So, because the function repeated itself, right, then the period is done and over in between the 2 asymptotes. That means that the middle point sits p halves on each side. So that's why I take whatever period we computed and I divide it by 2 to add it to the midpoint here. All right, so now let's see what this graph looks like. I know that there are 2 asymptotes at negative pi and positive pi. So I'm going to say 3 squares to the left and to the right to get to a pi. So negative pi and positive pi. Now if you take a look, right, since midpoint is in 0, 0. If you take a look, you have pi to the left and pi to the right. Pi plus pi is 2 pi, right? We have 2 pi for the period in this particular problem. All right, so the only thing that it's left is to put the squiggle through. It has to go through the middle point, has to follow the asymptotes, but it has to be flipped. So it will actually go this way. And now, whatever you see, this kind of curvature over here, just -3 and +3, it doesn't really matter where you put them, but it's at this curvature here, right? You see how it kind of curves downward, and then the same place over here kind of curves upward. That's where you put your 3 and -3, because that's the amplitude for this particular problem. And there's your graph of tangent. Now, if someone says, well, I would like another one, that's not a problem, because you can just count 6 squares, 1, 2, 3, 4, 5, 6, and you can put another vertical asymptote, put another midpoint, and draw the same graph in again. So once you have your principal period graphed, the rest of these are really, really easy, because they all repeat, which is what the concept of the period is, right? Periodically, you do something periodically. The frequency is also related to it. And yeah, that's it. So I'm going to give you a tangent graph, and then we'll talk about the cotangent, which actually has something that no other um, trig function has. So it's like 1 versus 5, right? But before we get to that one, let me put one of these tangent functions for you to try. And let's go with problem 12. So try y equals tangent of x minus pi over 4. I'm going to mute myself and let you work on it. I'll be back in 5 minutes, and we'll talk about the problem. So have fun. And, oops. Welcome back to our tangent and cotangent graphs. So let's graph this tangent and then move to cotangent. A is equal to 1. B is equal to 1. C is equal to pi over 4. And D is 0, which is the midline, is the x-axis. Right, so when this is equal to 0, that's x-axis. We don't need to move anything up or down. Now, we have the period to be pi divided by b, so the period stays unchanged. Awesome. The midpoint is going to be the parenthesis, which is the argument, right? The whole thing over here is called the argument of tangent, equal to 0. So x equals pi over 4. And the asymptotes are going to be pi over 4, which is the midpoint, plus pi over 2 and minus pi over 2, right? So those are the two different. So this is 3 pi over 4 for one of them, and minus pi over 4 for the other one. Again, your period is pi, half of pi is pi over 2, so that's what we are adding and subtracting on the midpoint to get, right? So you will have that, and we have the two of these. Good. So now we are going to draw our line. We're going to put this y-axis. And again, yes, we have pi over 4. But guys, again, I don't care. Those are, for me, those are tick marks. So what do I have? I have one tick mark to the left, negative pi over 4. I have one tick mark to the right, pi over 4. And then also 3 pi over 4. That's it. I have a negative 1, positive 1, and positive 3. Those are the three numbers. The two on the outside are asymptotes, vertical asymptotes. And the one in the middle is the midpoint. It's not flipped, which means it's going to go, come on, it's going to go down, it's going to go up, and there's your principal tangent. You can keep repeating this as many times as you want. And that ends the tangent graph. Oh, I forgot to mention again that curvature. So we'll put 1 and negative 1, right? Our amplitude. I almost forgot about that. And I think that's it. That's it for the tangent. So tangent is a little bit different than sines and cosines. And the reason is it has asymptotes. I mean, secant and cosecant have asymptotes, but we generally go back to sine and cosine to make comparisons. So tangent has asymptotes, and its period is pi, not 2 pi. That's also different than sines and cosines. But as sines and cosines, it will also repeat forever and ever and ever. And we still have the same thing like with sine and cosine when you take the parentheses set equal to 0. For sine and cosine, when you set it equal to 0, you find your start point. Now you find your midpoint. And how do we know we're supposed to set it to 0? Where if you take a look at what I call the vanilla graph, the parenting graph, the default case, this one over here, when you take a look at that one, you see that the midpoint goes through 0, 0, right? So when you have what I call a vanilla tangent, right, x as a function, you see that the argument is x equals 0. That's exactly there, right? So that's why we're setting it equal to 0. So period is pi, midpoint, you take the argument equal to 0, and then asymptotes, you just take, once you calculate your midpoint, you now calculate to the left and to the right the asymptote, and you are done. Now, I'm not supposed to cross this A, because amplitude is still important, obviously, but it's not humanly possible to do a great job in graphing it. So we just kind of draw the tangent line and then go with we draw the tangent line, and then whatever that curvature is, right, where it starts going up quickly or down quickly, that's where we put the amplitude. But again, it doesn't impact much on our graphs. All right, so cotangent, and we are done. And this one is different. Cotangent graph, and you have y equal a cotangent bx minus c plus d. So it's similar to tangent, but the midpoint calculation is completely different, and that's why it tends to be sometimes tricky. So cotangent x is cosine x over sine x. So now, anytime when sine has a 0, cotangent will have a vertical asymptote. So now let's take a look at the vanilla graph, right? We always take a look at the vanilla graph first, and then we're going to start with 1.6 shenanigans to move it left, right, and so. So let's go and do this. And we have asymptote, obviously, at 0. Let's say let's go 4. Have another asymptote. Another 4. Have another asymptote. And these are our 0, pi, and 2 pi, which we see on our sine graph. Now, cotangent will also have a midpoint, just like tangent, but it's opposite. When you draw, it's going to go like this, right? Remember the tangent went the opposite way? Tangent went this way. So the cotangent is going to go opposite way. So I'm going to now draw one more. And what you see here are two periods. Oh, two periods, right? So period is still pi. Formula for period is still pi over b. Nice. The curvature, right, is still going to tell you where a is, and negative a. Right, so that's all the same as tangent. Where is the problem? Let's write it in blood. The problem is the middle point. You see, now this is the only one out of 6 that has argument equals to pi over 2. All other 5 are equal to 0. This is the only one that has a pi over 2 there. So, and everything else works the same. You have your vertical asymptotes after this, right? And that's going to be middle point plus minus half of the period. And go from there to get the two asymptotes and everything else. So everything pretty much is the same as tangent. It's opposite to draw, right? It doesn't start from bottom up, it starts from top down. And oh, by the way, if you have a negative, right, then it would look like tangent. It's still not tangent, guys. Tangent is centered at 0, right? Tangent would go like this. That's the original tangent. It's not just flipped, it's also shifted to the left. So it's not just a flip, it's a shift as well. So we have to be careful about that. All right. So let's take a look at the cotangent example. Let's start with something that is vanilla and then upgrade. So how about negative 2 cotangent pi over 4x? Problem 22. Negative 2 cotangent of pi over 4x. Okay. Big fat flip, so we don't forget it. Amplitude is 2. B is pi over 4. C is 0, D is 0. Great. Immediately do the period. Pi over 4. That's a 4. So period is now 4. Okay, we can deal with that. And I need my midpoint. Now midpoint is pi over 4, x equal to 0. Sorry, equal to pi over 2. What am I saying? Pi over 2. That's what's different for... So all other functions are equal to 0. Cotangent is the only one that is equal to pi over 2. And this calculation is x equals to 2, obviously, right? Because when you multiply pi over 4 by 2, you get pi over 2. Okay. Now, I can get my vertical asymptotes as middle point is 2 plus minus half of the period. So that's 2 plus minus 2. So one vertical asymptote is at x equals 0, and the other is at x equals to 4. Okay, that's good, because in between two asymptotes, you should have a whole period. Yes, I do have the whole period in between two asymptotes. Nice. So we are going to draw this now and decide on my scale. Maybe 1, 2, 3, 4. Asymptotes for me are always red. There we go. And y-axis, right? That's x equals 0. So I have two asymptotes, and I also have my middle point at 2. Again, d is equal to 0, so it's not shifted up or down. So we are working on x-axis, actually. Perfect. I have everything. I know that my midpoint here at 2, my asymptotes at 0 at 4, so we're all good there. The only thing that I should not forget is the flip. So this one is going to look like a tangent. It's not a tangent, right? It's a cosecant graph. So it's a cotangent graph. Tangent goes through 0, 0. There we go. That's a cotangent. And it's flipped. Now, this curvature here, we'll call this 2. We'll call this negative 2. That's, just put it somewhere. I mean, don't put it here on top or too far down. Just try to match the curvature, right, somewhere in there. All right. So let's have one for you guys to try, and then we can call it for this lecture. Problem 24. Y equals 3 cotangent x plus pi over 4. So that's a problem 24. I'm going to mute, and I'll check back with you in a couple of minutes. All right, let's check the work, and I guess be done with this one. A is equal to 3, B is equal to 1, and we just need D, and D is 0. This C part will be the part of your calculations for MP, so we don't care, right? Period is pi divided by 1, so period remains pi. The midpoint is the parenthesis, but remember, it has to be set to pi over 2. And when you subtract pi over 4, you get pi over 4. Now, the vertical asymptotes are going to be the midpoint plus minus half of your a period up there, which is pi, so pi over 2. And you are getting two vertical asymptotes, x equals negative pi over 4 and x equals 3 pi over 4. We already had these asymptotes before. Again, we don't care that are quarters or thirds or whatever. We are just counting tick marks. One tick mark to the left for negative pi over 4 and 3 tick marks to the right for positive 3 pi over 4. So we don't have to freak out on those. So these are the tick marks. 1 tick mark to the left, 3 tick marks to the right. Now they happen to be pi over 4. So, okay. Those are the tick marks. And the 2 tick marks on sides are asymptotes. So the ones that are on out. And the middle is the midpoint. There is no flip here, so it's a cotangent, which means it's going to go up. This is a big wide graph. Goes up and goes down. And this is where we're going to put 3 and negative 3. Ta-da! That's it. We have everything labeled. Well, I didn't put X and a Y, but other than that, we have everything labeled, and the problem is complete. A lot of this stuff, guys, is just you practicing this over and over and over again. The box method, I mean, you do have these videos so you can review the box method for sine and cosine and ultimately secant and cosecant, because you still graph sine and cosine and you just flip inside out the graph once you're done graphing. The only one that you have to be careful with tangent and cotangent because their period is not 2 pi, it's pi. So that's one of the things. And then the cotangent is the only one that sets for the point calculation, that sets it equal to pi over 2. The other 5, they all set it equal to 0. So that's the only difference between these. And if you didn't like any of these methods, read the book. They have different methods there. Or just surf YouTube until you run into someone explaining these graphs the other way. I like the box method because it bounds the space in which the function has to sit, and I just need to connect the dots, just like the 5-year-old's coloring book, and yeah, that's technically what it is. It's connect the dots from that point on. You don't have to color though. That's good, right? Questions, concerns, anything regarding cotangent? I guess too easy. All right, so we'll say bye, and I'll see you later for the inverse.